So, welcome to this lecture, the next lecture in pattern recognition. We have been looking at estimation of density functions. So, to briefly recap what we have been doing, for the last few lectures, we have been looking at estimation of density functions given IID samples from the density. We have seen basically two methods of estimation. One is maximum likelihood estimation, and another is Bayesian estimation. In each case, we have seen how one derives these estimates and also seen many examples. The idea has been that given the estimated densities, we can implement the Bayes classifier. So, after seeing how Bayes classifier can be implemented, we have been spending all our time on figuring out how to estimate the class conditional densities, which were reduced to a problem of from a particular density, if you are given IID samples, how do I get the parameters of the density. Okay. Now, after that, we have been looking at some general issues in estimation. So, end of last class, after looking at various issues of Bayesian estimation, I briefly introduced the idea of the exponential family of densities. This is a very special family of densities, and most general densities belong to this class. So, this class will see this in more detail, and will also look at a few general issues in density estimation. Okay. So, to recall, we introduced the exponential family of densities last class. If you take a density model with a parameter eta as f x given eta as h x into g eta into exponential eta transpose u x, where u x is some function of the data, some function of x. Okay. Eta could be a vector, the parameters can be more than one in the density, and similarly then u will also be a vector function. But essentially any density that can be written as a product of a term that involves only x, a term that involves only the parameters eta, and another exponential of eta transpose u x, that is eta 1 u 1 x plus eta 2 u 2 x and so on, where u 1 x u 2 x so on are some pre-specified functions of x. Such a density is called an exponential family of density. The second line in the equation tells you why, because I can always write it as exponential of some of different terms, one term involving only x, one term involving only eta, this should have been eta not x, and one term involving eta and u of x. Okay. Many standard densities such as Bernoulli, binomial, Poisson, gamma, beta, all of them can be expressed in this form. As a matter of fact, among the standard densities, the only density that cannot be expressed in this form is a uniform density. Otherwise, most other densities can be expressed in this form. Last class we saw that the Bernoulli density can be written in this form, where eta happens to be ln p by 1 minus p. Normally, we think of p, the probability of success, as the parameter in Bernoulli density. Instead of that, if you take the parameter eta to be ln p by 1 minus p, then the mass function of Bernoulli can be expressed in the right form, with h x being 1, g eta being 1 by 1 plus exponential eta, and u x as x. So, Bernoulli belongs to the exponential family, the details we saw last class, and as I said last class, such an eta is often called the natural parameter for the Bernoulli model. Similarly, for all the other things expressed, when a density is expressed in the exponential family form, the corresponding eta is called the natural parameterization for the density. As another example, Gaussian density can also be expressed in this form. I have skipped the algebra. Algebra is quite straightforward, so you can complete the algebra. This is the standard Gaussian density on by root 2 pi sigma square exponential minus 1 by 2 sigma square into x minus mu whole square. It can be expressed like this, where the natural parameterization becomes eta 1, there are two parameters now, just like mu and sigma, now they become two parameters. Eta 1 is mu by sigma square, eta 2 is minus 1 by 2 sigma square. As a matter of fact, there is a one-to-one correspondence between the eta parameterization and mu sigma parameter. Given a mu and sigma, there is a unique eta 1, eta 2, and similarly given a eta 1, eta 2, there is a unique mu sigma. So, because this is an invertible transformation. But if I choose these etas as the parameters, with u1 x as x and u2 x as x square, one can write the Gaussian density in the required form. So, there is exponential eta transpose u x, there is something that is a function of only eta, and a constant which you can think of as part of g eta or part of h x. Okay. So, Gaussian density can also be expressed in the form needed for exponential family, and hence Gaussian is also a part of the exponential family. Okay. Like this, we can show that many standard densities belong to the exponential class of densities. Now, why do we consider this particular form? A density that is in this form has some interesting ways of writing of doing maximum likelihood estimates. So, let us say we want to do ML estimation of the parameter vector eta for a density from the exponential family. So, take any density from exponential family, which we can write as f x given eta as h of x g eta exponential eta transpose u x, and let us say we want ML estimation. So, for ML estimation we have to form the likelihood and then differentiate the and maximize the likelihood to find the ML estimate for eta. So, given that this is the form of the density, the likelihood will be what? Product of this, product of f of x I given eta I is equal to 1 to n. So, product of this with x replaced by x I and product I is equal to 1 to n. So, I get one term from this, product of h x I is equal to 1 to n. G eta does not depend on x I, so I get g eta to the power n, and because it is exponential, it goes into this as a summation. So, it becomes eta transpose summation I is equal to 1 to n u x I. So, this will be the data likelihood. Now, if I take log likelihood, that is log I get my log likelihood for eta as this is some term. So, I get log of this plus n log of this plus eta transpose u x I. Now, this is a term that does not depend on eta, and because we want to maximize the log likelihood with respect to eta, any term that does not depend on eta is of no consequence to us. So, I wrote it as some k. So, the log likelihood will be k plus n times ln g eta plus log of this will give me eta transpose u x I. So, this is the log likelihood where k is a term that does not involve eta. Now, to find the ML estimate, I have to maximize log likelihood. So, to maximize log likelihood, we take the gradient of this with respect to eta. Remember that eta could be a vector. So, in general, we take gradient of this with respect to eta and equate it to 0. So, if I take gradient, this term will go, I get n times gradient of ln g eta and I get summation u x I when I take gradient with respect to eta. So, that will be the gradient because I have to equate gradient to 0. If I equate gradient to 0 and solve, any ML estimate would satisfy this equation. Minus gradient with respect to eta of ln g eta is equal to 1 by n I equal to 1 to n u x I. Right. I get n gradient ln g eta plus summation u x I is equal to 0. So, solving that we get this. Of course, I can simplify this gradient by differentiating once. So, that gives me minus 1 by g eta into gradient of g is equal to 1 by n summation u x I. So, if I have any density in the exponential form, then I will know the function g eta and the functions u x. So, then solving these for eta, okay, eta at ML, I would get the ML estimate, which means for all densities that belong to the exponential family, we have a simple and uniform procedure for estimating densities. Right. So, all exponential family densities give rise to the same set of equations. The only thing that changes is the function g, the functional form of g and u will change depending on individual densities. Once I put every density in the exponential form, in the exponential family form, there is one set of equations that define the maximum likelihood estimate. This is one interesting aspect, but there is another interesting aspect. Right? What is that? To obtain the ML estimates, we have to solve this equation. Right? In solving this equation, I do not need individual xi. If somebody gives me summation I is equal to n u x I, that is good enough. So, the only way data affects my ML estimate is in terms of I is equal to 1 to n summation u x I. Right? To obtain ML estimates, we do not explicitly need all the data. We only need summation u x I. Right? We say that such such UXI are called sufficient statistics for eta. We will currently precisely define this, but what it means is to obtain ML estimates for at least for the exponential family, it turns out that I do not need individual data explicitly, but I only need certain functions of the data. Okay. So, such functions are called statistic, and in this particular case, because they are sufficient for estimating eta, they are called sufficient statistic. We will currently define it formally. So, let us define sufficient statistic. A statistic by definition is any function of data, given data x1 to xn, any function of x1 to xn is called a statistic. So, data is x1 to xn. So, a function of x1 to xn is a statistic. A statistic S, which is a function of x1 to xn, is said to be sufficient for a parameter theta if the density of D, that is the data, conditioned on the statistic con theta is not a function of theta. Essentially, we are looking at parameterized form of densities. So, if I want the data likelihood, that is the joint density of x1 to xn, it depends on theta. What this says is that the conditional density of data conditioned on the statistic is no longer dependent on theta. So, in some sense, the statistic S brings in all the information about theta that I need to know. So, if I have S, the density no longer needs the value of theta. So, in some sense, whatever information data has about theta is only in terms of the sufficient statistic. Okay. That is the reason why it is called sufficient statistic. So, once again to repeat, a statistic S is said to be sufficient for parameter theta if the conditional density of data given the sufficient statistic is no longer a function of theta. Okay. As you saw in the ML estimation, we do not need all the data explicitly, the sufficient statistics would do. That is how we motivate the sufficient statistic. As you saw in the ML estimate for exponential family, if somebody gives me these functions summation I is equal to 1 to n uxi, which are functions of the data, that is all I need to estimate the etas. Right. So, that for example, will be sufficient statistic for the exponential family of densities. Now, same thing we can see in Bayesian framework also. In Bayesian framework, because I think of theta as a random variable, I can say S is sufficient if the conditional density D given S and theta is that is conditioned on S, D is independent of theta. So, the conditional density D given S comma theta is same as conditional density D given S. Once again, I will caution you that, as I said right in the beginning of all these estimation lectures, when we say density, it could be either density or mass function. We are talking of both continuous and discrete random variables together. So, even though I keep using the word density, it could be a density function or it could be a mass function. Okay. So, in Bayesian framework, if S is sufficient, then conditional density of D given S and theta is same as conditional density D given S. Now, what does this give us? Now, if I want to in Bayesian density always find Bayesian estimation and always find the posterior density. So, posterior density of theta given let us say both S and D, using Bayes tool it will be density of D given S theta, f of theta given S by f of D given S. Now, if S is sufficient, f of D given S theta is same as f of D given S. So, this becomes f of theta given S. That the posterior density, that is density of theta given D and S is same as density of theta given S, which means if you give me S, I do not need the data. So, that is the basic motivation for defining sufficient statistic. Right? If f of D given S comma theta is not dependent on theta, then both in maximum likelihood and Bayesian framework, if you give me the sufficient statistic, the rest of the data is not important, at least as far as estimating the parameter is concerned. Okay. So, let us look at a example of a sufficient statistic. So, let us consider Poisson distribution, the sum distribution I have not considered so far. So, I have just we could have considered with any of them. So, I just considered Poisson. So, this is the Poisson mass function with lambda as the parameter and x takes value 0, 1, 2 all the way up to infinity. Okay. So, let S be a statistic. We think of S as a random variable which is a function of the IID random variables x1 to xn and any specific value taken by S as little s. So, little s is S applied on the specific data we have. Okay. Just so that the notationally things are clear. So, now let us show that for Poisson distribution this is sufficient statistics. See, for Poisson distribution we know already that lambda is the mean of the distribution, and hence we know the ML estimate is sample mean, and if you just give me the summation xi, I can calculate sample mean, right. I do not need the individual xi. So, we know that this is sufficient for estimating lambda. So, let us show that S is sufficient as per our definition. So, to show S is sufficient, what do you have to show? We have to calculate the conditional density of D given S and show that it is no longer a function of lambda, because we have to actually calculate conditional densities. Here it is worthwhile for us to be a little bit precise in our notation. So, let us denote this thing, let us leave lambda, lambda is only a parameter, we are in the maximum likelihood framework here. So, I do not have the condition on lambda. So, what did the conditional density of D given S mean? If x, the vector x, that is x1, x2, xn is a random variable and this x is the actual value taken by it. So, if the conditional density x given S evaluated at the value x given little s. Okay. So, this is the conditional mass function. We have to show that this conditional mass function does not depend on lambda, even though the mass function of x depends on lambda, okay, and hence mass function of D depends on lambda. Okay. So, let us calculate this conditional mass function. What is this conditional mass function? Is a mass function. So, is the probability x1 is equal to x1, x2 is equal to x2, xn is equal to xn, condition on S is equal to S. So, P A given B is P A B by P B. So, that is probability x1 is equal to x1, so on, xn is equal to xn, S is equal to S divided by probability S is equal to x. That is the conditional mass function. Now, the little s, as you seen, is the capital S function applied on little x1, x2, xn, okay. That is nothing but x1 plus x2 plus xn. So, this probability, as a matter of fact, this probability is same as the probability x1 is equal to x1, x is equal to xn when little s is equal to x1 plus x2 plus xn, otherwise of course, it is 0. So, this probability can also be written as x1 is equal to x1, x2 is equal to x2 all the way up to xn minus 1 is equal to xn minus 1, and xn is s minus the remaining thing, because sum of all xi should be equal to s. So, the numerator I can write like this. Now, I can write the denominator also like this and sum over xi, that will give me the marginal of s, right. This will give me the conditional of x1, x2, xn and s, and hence if I sum over xi, that gives me marginal of s. So, I can write the denominator also like that. Now, we have to look at this expression, how to get this probability, right. Probability x1 equal to x1, xn equal to xn minus 1 equal to xn minus 1, xn is equal to this. How do we get this probability? So, x's are the data are IID. So, each of them is Poisson distributed. So, say probability x1 is equal to x1 will be e power minus lambda 1 by x1 factorial into lambda to the power x1. So, I have n such terms. So, I get e power minus n lambda. I have 1 by x1 factorial, x2 factorial all the way to xn minus 1 factorial. Up to xn minus 1, I get lambda to the power summation xi is equal to 1 to n minus 1. For the last term, I get 1 by this s minus summation xi factorial, lambda to the power that. Okay. Now, I got lambda to the power summation xi is equal to 1 to n minus 1 here. Here lambda to the power s minus the same summation. So, those two together will give me lambda to the power s. So, that gives me lambda e to the power minus n lambda, lambda to the power s, and something that only depends on xi. All this depends only on xi. This also depends only on xi, because s is summation xi, right. So, this factor only depends on xi's, this factor only depends on xi's. So, this entire thing becomes e power minus n lambda, lambda to the power s into hx, where hx is a term that depends on xi, but does not depend on lambda. Okay. So, now let us put that in the previous equation. So, I get my previous equation was this. So, I substitute both in numerator and denominator for this value. This value is this. So, if I substitute that in both numerator and denominator, I get e power minus lambda n lambda, lambda power s into hx, that bold x is actually x1, x2, xn, and some more xi of the same thing. Okay. So, now the lambda terms which are no longer dependent on xi will come out of the summation and cancel with the corresponding lambda terms in the numerator to give me this. So, this conditional density now is no longer dependent on lambda. As a matter of fact, it happened because the data likelihood was factorized, so that the terms that come with lambda can at most depend on s, but not on individual xi, and the things that depend on individual xi do not depend on lambda. This factorization is what helped us to pull out the lambda terms from the summation in the denominator, and that cancels with the numerator. Okay. This cancellation is what actually made that s into a sufficient statistic. We will see that this is not a special case. This is how sufficient statistics come up. Any case, in this example, what we have shown now is that the summation xi is a sufficient statistic for lambda in the Poisson distribution, and we know that if you give me summation xi, I can get ML estimate for lambda even though I do not know the individual xi. So, it is in that sense sufficient. Okay. Now, we can characterize the sufficient statistics exactly. When is a statistic sufficient? It is known as factorization theorem. The theorem says the following: a statistic S is sufficient for theta if and only if the likelihood function, okay, f of d, that is joint density or mass function of x1 to xn, can be factorized into product of two factors. One factor involves only s and theta and another factor involves d. That means, there is no factor that involves individual xi's and theta. Anything that depends on xi's is all bottled up in this h function, just like the h function we had in the example. And another factor, the only way data enters in this fraction is through s. So, if the likelihood function can be factorized like this, then the statistic s is sufficient for theta. Okay. This theorem is an if and only if theorem, that is, if s is sufficient, then the likelihood can be factorized like this, and if for some statistic s the likelihood can be factorized like this, then that s is sufficient. Where sufficient is, as you defined earlier, conditional density of d given s and theta is not a function of theta. Okay. So, in our example, we saw how a similar factorization happens when s is sufficient. Okay. Now, we will see how it enters in the exponential family. This is the density model for any member of the exponential family. So, if I now take the likelihood, that is product of xi given eta I is equal to 1 to n. So, I get g eta to the power n exponential eta transpose summation u xi, this is one factor, and summation I product over I h xi, this is another factor. It is exactly in this form, g s theta into h d. So, what is put in this big square brackets is g s theta. This depends on, here theta is eta, it depends on eta and s, the summation u xi, which is the statistic, but does not depend on individual xi, and the factor that depends on individual xi does not involve eta. So, you got g s theta h d factorization, which tells me that s is equal to summation over u xi is the sufficient statistic, because you get the needed factorization. So, for all densities in the exponential family, summation over u xi is the sufficient statistic. Just one special thing that you should note, we already said eta could be a vector and u's could also be a vector, then summation over u xi would be a vector. So, a sufficient statistic could be a vector. So, what we mean is, for the exponential family, this vector statistic summation over u xi is sufficient for the vector parameter eta, because that does not mean that the first component of s is sufficient for the first component of eta and so on. All components of s may be needed for any component of eta. We are talking in terms of vector quantities. So, the vector statistic is sufficient for the vector eta. Okay. That is how the factorization works. Okay. Now, we will sketch out the proof for the factorization theorem. We will do it only for the discrete random variable case. The proof is similar for the continuous case. I will just mention where the difference comes later on, but it is a little more complicated. So, we will do it only for the discrete random variable case. Okay. So, to recall, data is x1 to xn, little s is the value of the sufficient statistic s x1 to xn, s is a function of x1 to xn. So, I said factorization theorem is different only if there are two things I have to show. If S is sufficient, then the likelihood function factorizes, and if the likelihood function factorizes, then S is sufficient. So, let us do the first part. Assuming that S is sufficient, let us show that the likelihood function factorizes. Okay? Because we are considering discrete random variables, the density is actually mass function nothing but probabilities, joint probabilities. Since S, little s is actually equal to S applied on x1 to xn, probability x1 is equal to x1, xn is equal to xn is same as probability x1 is equal to x1, xn is equal to xn, s is equal to s, right. This is what we already used in the example, but it is good to remember this, because s is some function of x1 to xn. So, if x1 takes value little x1, xn takes value little xn, this function takes value s. So, the event that x1 is equal to x1, xn is equal to xn is subsumed by the event that s is equal to s. So, whether I add this s equal to s, the probability does not change. Okay. So, this is something that is worth remembering, which is needed in proof again and again. Okay. What is it to show? To show that we are assuming that s is sufficient and showing that the likelihood function factorizes. So, this is the likelihood function. Because we are considering the discrete random variable case, it will be probability x1 equal to x1, xn equal to xn, where theta is the parameter. This, as we seen, can be written as the same probability with s is equal to s, condition of theta. Now, you think of x1 is equal to x1, xn is equal to xn is some a, s has some b, and theta is some c. Then is a b given c, probability of a b given c, which can be written as a given b c into b given c, right. So, I can write it as probability s is equal to s given theta, and probability x1 equal to x1, xn equal to xn, condition on s is equal to s and theta. Okay. Now, because I have assumed s is sufficient, this factor, this is nothing but f of d given s and theta, which is not a function of theta. Okay. So, I can write this as simply I can remove this theta from here. Okay. This happens because we are assuming s is sufficient. So, now, because this can be a function of only s and theta, is probability s is equal to s given theta. So, this is some g s theta. Now, this does not involve theta, this is x1 equal to x1, xn equal to xn, probability given s is equal to s is also a function of x1 to xn. So, this probability whatever it is can only depend on x1 to xn, but does not depend on the parameter theta. So, f d given theta is given by a product of some function that involves s and theta, another function that involves data, but does not involve theta. Okay. So, this means the likelihood is factorized when s is sufficient. So, that completes the first part of the proof. Okay. The theorem states that s is sufficient if and only if the likelihood factorizes. What we shown here is that if s is sufficient, then the likelihood factorizes as needed. Okay. So, that completes the first part of the proof. The second part, we have to show that if the likelihood can be factorized, then s is sufficient. Okay. Then the proof will be complete. So, let us show that also. If the likelihood can be factorized, we show that s is sufficient. As we seen earlier, this is something that we will keep using. So, I am just reiterating this. To show s is sufficient, we have to show it from definition, that is the conditional density of d given s is not a function of theta, that is what we have to show. So, under the assumption that the likelihood function factorizes, we are going to show that the conditional density of d given s is not dependent on theta. Okay. Okay. So, let us write the expression for conditional density d given s theta. So, this is a conditional mass function. So, it will be joint of d and s by marginal of s, that is what I wrote here, because mass function, this is the joint of d and s, probability x1 is equal to x1, xn is equal to xn, s is equal to s, and this is the marginal of s. Okay. The theta comes because that is the unknown parameter. Okay. Now, the marginal of s can be obtained by summing over the joint. So, I can take the joint of x1, x2, xn s and sum it over all possible xi, I will get marginal s is equal to s. Right. So, I just written this marginal with this probability s equal to s as a true, obtained as a true marginal mass function obtained by summing out all the other variables from the joint mass function. Okay. Because as a matter of fact, this summation need be only on those x1 to xn, such that s of x1 to xn is s, because the probability x1 is equal to x1, x1 is equal to xn and s is equal to s, and s is a specified function of x1 to xn. So, for any given values x1 to xn, this little s is not equal to capital S of x1 to xn, then this probability is anyway 0. So, actually the summation goes over only those xi, such that s of x1 to xn is s. Now, we have in this part of the proof, we have taken that the likelihood function factorizes. So, this is the likelihood function. Okay. It can be written as g of s theta into h t, right, because this is the likelihood function and it factorizes. I can now substitute this in both numerator and denominator, right, and when I do that, f d given as theta is g s theta h d by summation or xi g s theta h d. D is actually x1 to xn. So, that is where these xi's are, the summation indices. Now, the g s theta will come out of the xi summation and cancel with the numerator, and that will give me h d by summation h d. I hope you can see the similarity with the example. That is exactly how we how we showed S is sufficient in our example. That factorization, as I told you at that time, is what is at the heart of it being sufficient. So, once again, as we can see, the conditional density is not a function of theta, okay, thus showing that S is sufficient. Okay. So, this completes the complete proof. We have shown both halves, and essentially a statistic is sufficient if and only if the joint mass function. Let us look at the theorem again. The theorem is certainly more important than the proof. A statistic is sufficient if and only if the likelihood factorizes into a factor that is dependent only on s and theta, another factor that may be dependent on individual data. Okay. So, we have seen we have proved both parts of this theorem, the so called factorization theorem that characterizes sufficient statistics. So, one way of looking at sufficient statistics is that they give us good compression of the data. That is, if I am only interested in estimating parameters, then I do not need to remember all the individual x. Right? I only need to remember summation over I u x I. Right? So, that is a kind of data compression for parameter estimation. So, if I am estimating sample mean, I do not have to remember each of the x's. I can keep a running sum, and the sum of all the data I have seen is the only thing that affects my sample mean at any point of time. Right? So, sufficient statistics give us a good compression of the data. Okay. Having said that, we should also realize that the factorization we talked about is never unique. We are saying S is sufficient if the likelihood factorizes into two factors, one dependent only on S and theta, another dependent on the individual data, but not on theta. Now, given any such factorization, f of d given theta g s theta into h t, and given any other function of the statistic g 1 of s, I can rewrite this as g 1 s into g s theta h d by g 1 s, because g 1 s is only a function of s and s is a function of data. Once again, this is a factor that does not involve theta, that only involves the data, right. So, this is also a factorization. So, there is no uniqueness about the factorization of the likelihood into two factors, one involving the statistic and the parameter, another involving the data. Right? This does not necessarily cause any problems, but very often what one does is to, once you have a factorization, you take the factorization, the g s theta function, as a normalized value, right, which is called g tilde, sometimes called the normalized kernel. But so, if I take this, then this kind of simple non-uniqueness will not be there. Okay. There is another aspect of sufficient statistic which I will not go into in this course. Sufficient statistics are also useful in finding what is called UMVUE. If you remember, we talked about uniformly minimum variance unbiased estimators. Okay. Essentially, if I have any unbiased estimator and I take its expectation with respect to a sufficient statistic, a conditional expectation of the unbiased estimate with respect to sufficient statistic, condition on the sufficient statistic. The resulting thing also becomes a estimate, and that has lower variance. So, taking a conditional expectation, condition and sufficient statistic is one way of reducing variance, and if the sufficient statistic satisfies a few more conditions, then that is a way of finding uniformly minimum variance unbiased estimators. Okay. That takes us unnecessarily into estimation theory. So, we are not looking at this thing, but it is worth remembering that sufficient statistics also play a role in obtaining uniformly minimum variance unbiased estimators. Okay. Now, we will look at one other aspect of estimation. We have been looking at our maximum likelihood and Bayesian estimates as we derived all the estimates, but the way we derived them, we are assuming that all data is with us, right. We are just deriving some functions of the x1 to xn at the estimates. So, in a sense, this works only when all the data is with us, all the data is explicitly stored somewhere. Right. So, in that sense, sometimes these are called batch versions of the estimation method. Batch in the sense, I need to have all the data with me. Okay. So, for example, if the data is flying by as a stream, where I can only read one data at a time, but I do not have a place to store them, then the way we wrote our equations, it is not possible to implement the estimates. Okay. That is why these are called batch versions, where I need to store all the data with me. But that does not mean that these estimates always need to store all the data for working, right. We can have all these estimates in what is called an incremental or recursive fashion. Incremental means we look at data one by one. So, even if the data is flying by, I can look at only one sample at a time and still keep my estimates current. Okay. Such a structure for an estimate is called a recursive estimate. Okay. So, in a recursive estimate, what we assume is that the data samples, we get the data samples one by one, right. Not all of them are given to us, and we cannot store all the data, right. We have very limited storage. So, we can only look at each data, do some computation in our scratchpad memory, and keep only a few numbers with us, and data may be very large. We will not be able to store the data, and but still we want to always have the right estimate. Okay. That is, if we have an estimate with us after seeing n minus 1 samples, but I do not have the samples anymore, and then you give me one more sample, I should derive the estimate that you would have got with n samples, right. That is what a recursive estimate is about. We can always derive such recursive estimates, right. So, we can look at any of the estimates that were derived earlier and ask what will be the recursive forms for that. Okay. So, here is one simple example. As usual, let us take the example of sample mean. As we seen, sample mean is the ML estimate, is also UMV estimate for many parameters. So, for concreteness, for example, if we are estimating mean of a normal density, we know sample mean is the ML estimate. So, let us ask how we can do sample mean recursively. Very simple, this is the sample mean, right. I can rewrite the sample mean in this form, right. So, instead of adding all the n, I first add n minus 1, divide by n minus 1. So, I multiply by n minus 1 here. So, this gives me 1 by n into sum up to n minus 1, and then 1 by n into x n. This will give me the sum of all the ones up to n divided by n. Okay. Now, what is inside the brackets is the mu hat n minus 1. It is the sample mean or the first n minus 1 data. So, I can rewrite this as n minus 1 by n mu hat n minus 1 plus 1 by n x n. So, this is a recursive formula for sample mean, right. So, sample mean at the end of n is easily obtained if I know the sample mean at the end of n minus 1 on the next data item. Okay. So, many ML estimates obviously can be rewritten recursively like this, but we can actually do it in a much more general form for ML estimates. We will take a look at how to write recursive estimates in general like that. Before that, we will rewrite this recursive formula for sample mean estimator slightly differently. I can write this, as you can see, if I write this as 1 minus 1 by n. So, on the right hand side I have a mu hat n minus 1 and plus 1 by n into x n minus mu hat n minus 1, right. So, I can write the sample mean estimate as mu hat n is equal to mu hat n minus 1 plus 1 by n into x n minus mu hat n minus 1, right. These are the kind of iterative algorithms you might have seen in many places, for example, in a gradient descent algorithm or many other iterative schemes. So, if z is something that you are updating to an iterative scheme, is zn minus zn is zn minus 1 plus some step size into some something that depends on only the previous value and something that comes at n. Okay. So, this is like an error correcting or optimization algorithm. The fact that we can write the sample mean estimator's recursive form in this way, like an error correcting or optimization algorithm, is not accidental. It is true in a generic sense. Okay. So, in what sense is true, we will see now. We will generalize this idea, so that it applies to all maximum likelihood estimates. The ML estimation maximizes the log likelihood, right. Log likelihood is equal to 1 to n ln f x I given theta. If it maximizes that, it also maximizes 1 by n of that. So, essentially, to obtain the maximum likelihood estimate, I have to equate the gradient to 0, or just symbolically written the gradient as del by del theta or dou by dou theta of 1 by n is equal to 1 to n ln f x I given theta is 0. This is what the maximum likelihood estimate satisfies. Now, what I put inside the brackets looks like a sample mean of something, right. Xi's are IID. So, I can think of ln f of xi as some function of the random variable xi. So, 1 by n is equal to 1 to n of some function, let us say some h1 of xi. That is nothing but a sample mean estimate of expected value of hx, right. So, essentially I can take the derivative inside the summation. If I take the derivative inside the summation, then it is sample mean of dou by dou theta of ln f xi given theta, which are some functions of xi, right. So, I can take the derivative inside the summation, and if I think n is very large, essentially in the limit of large n, I can replace this sample mean by its expectation, which means I can say the ML estimate satisfies an equation like this. So, the dou by dou theta went inside, this 1 by n summation has become expectation with respect to x, these xi's have become x. So, expected value of x dou by dou theta ln f x given theta is equal to 0. So, let us call this some function h theta. Let us say h theta is expectation with respect to random variable x of dou by dou theta ln f x given theta. See, our samples x1 to xn are essentially IID realizations of this random variable x. So, this expectation is nothing is the sample mean is actually an approximation to the expectation, and at large n the sample mean 1 by n dou by dou theta ln f x I given theta will be same as expectation of dou by dou theta ln f given theta. So, the ML estimates actually satisfy this expectation equal to 0. Let us call this expectation function, because the expectation is only a function of theta. Let us call that function h theta. So, the ML estimate satisfies the function h theta is equal to 0. Now, let us define z theta to be dou by dou theta of ln f x given theta, right. That is what is inside the expectation, dou by dou theta of ln f x given theta. Because x is random, z theta is a random variable, right. So, z theta is random, and we have IID realizations of x, x1, x2, xn. So, I can calculate dou by dou theta ln f x1 given theta, dou by dou theta of ln f x2 given theta, because xn, x2 or so on are IID, those are IID realizations of z theta now. Okay. So, z theta is random and we have IID realizations of z theta. What are we interested in? We are interested in maximizing h theta, right, where h theta is expectation of what we call z theta, right. So, we are actually interested in maximizing h theta, which is expected value of z theta. However, we do not know h theta because we can't take that expectation, but we are allowed to see IID realizations of z theta. Okay. So, we have IID realizations of z theta, observations of z theta. Based on that, I have to actually not maximize, find the 0 of h theta. Okay. Because we are not actually maximizing, we want to solve h theta is equal to 0. So, we are actually not maximizing h theta, but we are solving for h theta is equal to 0. Okay. A classical algorithm for doing this is what is called Robbins-Monroe algorithm, which is actually a special case of what I call stochastic approximation algorithms. Okay. Once again, considering the stochastic approximation algorithms in all their generality will take us too far afield, but let us just look at, suppose I want to find solution to h theta is equal to 0. Okay. But I do not know h theta, but I only know z theta, and h theta is expected value of z theta. Okay. Such an algorithm is given by this. If I actually think of h theta as the gradient of something, which it is actually, right, h theta is actually gradient of something. So, in general, if h theta is gradient of something, that something is the log likelihood function. I want to maximize the log likelihood function, which is same as finding a 0 of the gradient. Now, what is my gradient descent algorithm? Theta n plus 1 is equal to theta n plus some small step size into the gradient. Okay. So, similar to that, the algorithm for finding 0 of h theta based on the observation z theta is same, theta n plus 1 because theta n is equal to theta n minus 1 plus some step size. If I had h, I would have put h of theta n minus 1 here, h is the gradient. So, then this would have been actually the gradient descent, but I do not have access to h, I only access to z. So, I put z there. Of course, z is random. If I actually put h is the gradient. So, if I actually reach a minimum or maximum, then h will be 0. So, there is a standard stopping point for the algorithm, because z is random, so to say z, because all I know is z is expected value, h is expected value of z, z is some noise corrupted version of h. So, even at 0 of h, z does not have to be 0. Okay. So, it is not quite clear what this algorithm does, but because we do not have h, we only have z, we put z in place of h and we put a step size. Now, if this has to converge, because we are not guaranteed that z will be 0 at the 0 of h, the only way it can converge is a n should go to 0, but a should not, if a n goes to 0 any which way it will not work. So, the step size a n has to satisfy these requirements. Firstly, a n has to be 0, because unless a n goes to 0, the algorithm does not converge anywhere, right. Unlike gradient descent, which can converge with small constant step size, here because even at the 0 of h, the corresponding z is not guaranteed to be 0, there is no such absorbing states for the algorithm, because z is stochastic. So, a n has to go to 0, but the idea is that a n cannot go to 0 too slowly. Essentially, we want a n to go to 0 slowly, okay, so that sufficient averaging takes place, but not so slowly that the algorithm does not converge. Because there are many other conditions for the algorithm to converge, but I have only given you conditions on a n. So, a n should satisfy a limit tending to infinity a n is 0, summation a n is equal to infinity, and summation a n square is less than infinity. So, a n goes to 0, okay, does not go to 0 too fast, but does not go to 0 too slow either. That is what these conditions mean. For example, a standard a n that satisfies this is something that varies as 1 by n. If I take a n to be c by n, then as n tends to infinity a n goes to 0. As you know, 1 by n is infinity, but 1 by n square is less than infinity. So, such an a n always satisfies this. So, essentially something like theta n is equal to theta n minus 1 plus 1 by n, z theta n minus 1 will be dou by dou theta of L f x n minus 1, right. That is what I will get if I take a n to be 1 by n, right, and that is exactly the recursive equation we had for the sample mean estimate. So, we can think of any ML estimate, because all ML estimates are essentially trying to find a 0 of h theta, where h theta is the expectation of this given IID observations of this what we call z theta. Right. We can always write such things in the stochastic approximation form. This will always be a recursive estimate, right, and that will be like the recursive equation we have seen for the sample mean. So, this is one generic way in which in the large sample case ML estimates can be approximately thought to be always having a recursive form. Of course, in specific cases such as the sample mean, we can get an exact recursive form. Okay. Now, the Bayesian estimates are even more inherently recursive. Okay. So, we'll to see that let us say that D superscript n denotes data of n samples. To show the recursive nature, would have a symbolism for how many samples the data involves. Now, I can write the data likelihood f d n is product I is equal to 1 to n f x I given theta. I can take the product of the first n minus 1 and then take the n separately. The first n minus 1 will give me f of d n minus 1 given theta. So, I can write f d n given theta as f x n given theta and f d n minus 1 given theta. This allows us to write the posterior density in a truly recursive form as follows. This is the posterior density f theta given d n using base rule is f d n given theta f theta. By normalizing constant is integral f d n given theta prime f theta prime d theta prime. I put theta prime here because that is a dummy variable, is not same as this theta which is there on the left side. Okay. Now, I can write f d n in terms of f d n minus 1 as we just now saw. So, I can write the numerator as f x n given theta into f d n minus 1 given theta into f theta. Once again, the denominator also same thing, integral f x n given theta prime f d n minus 1 given theta prime into f theta prime d theta prime. Okay. Now, this is the posterior density after seeing n samples. So, if I wanted posterior density after seeing n minus 1 samples, f of theta given d n minus 1 by this formula, I would get f d n minus 1 given theta f theta by some normalizing constant. So, let us choose some other dummy variable here, integral f d n minus 1 given theta double prime f theta double prime d theta double prime. Now, this thing, this denominator is some term that does not involve theta at all, because the thetas are all integrated out. So, as far as this is concerned, it is like constant. So, let us say in this equation, in the second equation here, I divide both the numerator and denominator by integral f d n minus 1 given theta double prime f theta double prime d theta double prime. Then in the numerator I get f d n minus 1 given theta f theta by integral of this, right, that becomes f theta given d n minus 1. Similarly, in the denominator I have f d n minus 1 given theta prime f theta prime by this normalizing constant. So, that becomes f of theta prime given d n minus 1. Right. If I do that, my f theta given d n becomes f theta given d n is f of x n given theta, that is already there. F of x n given theta is separately there in both numerator and denominator. Only the remaining thing that we are simplifying using this formula. So, f x n given theta f theta given d n minus 1 integral f x n given theta prime f theta prime given d n minus 1 d theta prime. This is truly recursive. If I know f theta given d n minus 1, I can calculate f theta given d n given only f x n given theta, that is the new sample. So, this is the recursive form for any general Bayes estimate, right. One way of looking at it is after seeing n minus 1 samples, we have f theta given d n minus 1. Now, that becomes the prior, so to say, that is the current prior density. Normally, in the posterior density, I get the likelihood here and prior here. So, I can think of this is at the end of seeing n minus 1 samples, my current belief about theta is f theta given d n minus 1, right. Now, you give me some more evidence, I use the new evidence f x n given theta and my current belief f theta given d n minus 1 to find my new beliefs f theta given d n, right. So, this is the recursive form of Bayes estimate, where f theta given d n minus 1 is essentially, so to say, the current prior for estimating f theta given d n. So, after seeing n minus 1 samples, your theta given d n minus 1 is the current prior while calculating the posterior when we see the next sample. Okay. Often this is termed the Bayesian learning of densities, because this is inherently recursive. As and when I see more samples, I keep refining my belief about the unknown parameter vector. That is essentially what this calculating posterior density in Bayes means. Okay. So, in this sense, Bayes estimates are also recursive. I should say also ML estimates are recursive to an approximation, where Bayes estimates are inherently recursive in this sense. That is why it is often termed Bayesian learning of densities. Okay. So, we will sum up today's class. We have seen some general features of estimation today. We have looked at the so called exponential family, which is a good representation for most standard densities. So, that we can think of all ML estimates of standard densities in a convenient general form. It gives the simple form for ML estimation for all densities in the family. Okay. And this form has motivated us to discuss the very important notion of sufficient statistics. Sufficient statistics are functions of data which are enough for estimating a parameter. That is, if I am given the sufficient statistic which is function of the data can be thrown away. So, in some sense sufficient statistic captures all the information the data has about the parameter value. Okay. So, using this exponential family example, we have motivated the idea of a sufficient statistic, then we defined a sufficient statistic, seen examples of sufficient statistic, and then we also stated the factorization theorem, which gives if and only if conditions for a statistic to be sufficient, and proved the factorization theorem. Then finally, we have seen that all estimates we derived can be put in recursive form. ML estimates become recursive by looking at them as a general instance of stochastic approximation algorithms, and Bayesian estimates are inherently recursive, leading to what is called Bayesian learning. Now, after this, we are more or less done with parametric estimation. In the next class, we will just look at one other interesting aspect of ML parameter estimation for what is called mixture densities, and then we will close parametric estimation and then look at non-parametric estimation densities. Okay. Thank you.